start recording. Okay, so what we did was we started to understand that a robot is very complicated. It's very complex and there's so many moving parts. But what you can do is you can start to take a robot and break it up into the individual subsystems, such that each subsystem handles something very specific, very particular, and the robot can then start to think of like performing an action as directing the subsystems to each take care of their own little piece of the puzzle. So what we did is we went through, I believe, two different subsystems. I think we started to go through the elevator subsystem last time. So we went over this intake over here, and then we went over the elevator. And I guess the idea of what would be really nice and what I'm trying to impart and kind of like organize or structure a system around this is to think of, to basically train our minds to, I mean, with engineering, right? You never have the same problem again, right? There's always going to be new variables, new pieces of information, and it's always going to be new. But the thing is that what we've developed here is we understood like what a class is. So programming in Java, it's a class. And as it relates to subsystems, we broke it down, as you can see for the elevator and the intake. We broke it down into very similar kind of like a checklist. So a subsystem can be thought of as properties and methods, right? That's what a class has inside of it. But the properties, if we drill a little bit further, we can think of properties as sensors, actuators. Actuators are like motors or pistons or kind of like something, a component that does something. And then other required variables that are going to be necessary. So for the intake, so we figured out that an intake needs a motor. So in this case, it was a Falcon 500 and a piston. So and to actuate the piston on the intake. So for example, here's the motor, which turns the actual wheel, and then over here is the piston, which kind of makes extends and retracts the intake. So those are the two properties, I guess you can call it. And then methods, we actually went through all of the different functions that this intake should be able to handle. So extending, retracting, intaking a ball, and exhausting a ball. And we started to drill a little bit deeper into what the underlying logic should be. And then over here on the elevator, right? So the elevator is a bit different. Elevator. So here's the elevator. The elevator is actuated by a single motor. So if we go back here, so the properties, so there's a motor. But then, as we discussed in our last call, there are very important sensors that are needed to make the elevator run. So the first sensor is we need an encoder. So an encoder tracks the rotation of the motor, so you can know precisely how much, not voltage, but how much distance the elevator has traveled. And then we went into, so an encoder isn't enough, because an encoder measures at its 0 points. I guess when the robot turns on, this inside, the piece that actually moves, this is called the carriage. And then the carriage if it's at its top, at its up position, the robot won't know that the carriage is at its top position. It'll know after it's booted on and the encoder starts reading values. It'll know, okay, I've gone down 5 inches, but it doesn't know the absolute set point for that. So for that, we need what's called the Hall effect sensor. And it's a little sensor, right? And what it does is it signals to the robot when there's a magnetic field nearby, and so i.e. a magnet. So the idea is that you put a magnet like somewhere at the bottom of the carriage, and then if you make the elevator go down slowly, you can keep, at the beginning of the match, you can keep making it go down slowly until the Hall effect sensor, which let's say is right here, when it triggers and it says, oh, I see a magnet. Now at that point, you can stop the motor and reset the encoder, such that at the beginning of the match, you can kind of like zero out the elevator. Does that make sense? Or are there questions before we continue?
Yeah, that makes sense.
Okay. So that's what we did last time, and then we went through kind of some methods on the elevator. So now, what I said in Slack was we would start to go over the what's it called? The swerve, how swerve actually works. And as I was playing around with kind of like generating ideas for the next few lessons, I think that swerve is not the right approach to do next. Because how we're actually going to use swerve is we're going to literally use the default methods that WPI-lib gives for swerve drive. We're not going to do any of the complicated like mathematics or anything like that. So I think what's more important to discuss and to do is to start to follow on last class, which is all about taking a robot, as you see this large robot here, and breaking it down into subsystems. And now I think we should extend that and start to see how in the program, how in the code, everything fits together. Does that sound good?
Yeah.
Okay. So yeah, because conceptually we went over what a subsystem is, and now let's just like drill a little bit deeper into that, and to actually get to a place where we can code. Cool. And I guess as a quick question, so I've kind of like presented one approach to learning how to program, which is it's like instead of starting with like hello world and like very basic things, and eventually like 6 weeks to build up to this is how robot programming works, I've come at it from like a top-down approach of like, this is a robot, here's how you start to think about subsystems, and as programming concepts come up, then we go into it. What do you guys think of this kind of approach? Is it better, or is it more of a struggle, or kind of like what is your idea behind how I've been going about teaching?
Actually, oh wait, my bad. You go first. Okay.
So, I think this approach is better than starting from the very basics, because we get to know firstly about like everything that the lab has to offer, and then how to put that into play. So, I don't know how to explain it, but I feel like this method is
Okay, great. And Kyle?
I completely agree because it's just you're jumping right in and you instantly get stuff that you could use like on the robot right off the bat, and you're instantly gaining experience instead of having to build up to that.
Yeah, and then it's like hopefully the idea is that you're starting to build an intuition about how to think about robotics in terms of the code, and not just like these are the lines that you have to write. That's really like my main goal. So I hope that, and if anything is not intuitive, like we're gonna actually get into robot, or I mean like programming design principles, and it might get technical. So I want you guys always to ask yourself the question: is this intuitive? And if not, we need to take a step back. Okay. So please be vocal about it, because this is like very important. Okay.
Got it.
Okay. With that being said, right? Let's over here we have subsystems. Okay. What is the point? What is the purpose of a subsystem? So we've gone over kind of the details. Now let's take a step back. And what is a subsystem? Like what is it? Think of a subsystem as a black box. Okay, so this is something that So I went to UCLA for engineering, and I remember struggling through one of my classes. I don't remember which one. And it was like there were super complicated equations, like using calculus and differential equations and stuff like that. And it got really complicated. And I had to take a step back, and this is one of the most important things that I learned at UCLA, is you can, however complex this might be, you can say, okay, pretend for a minute I know nothing about it, and it's called the black box. Okay. And let's think of the subsystem in this case as a black box. I don't know what's inside of it, but I know that there's inputs and outputs. And then thinking in this way is actually very, very helpful. So going back to here, if we say, okay, this subsystem, let's say any subsystem, not an elevator, not an intake, but a subsystem, what are the inputs to the subsystem? And what are the outputs? And if
the input would be code, correct?
Okay. And what's the output?
An action.
Mm-hmm. So I'd like to think of the subsystem as driver intent, or like what we want the robot to do. So we want, and then the output is kind of like robot doing something. Okay. So the input is what we want the robot to do. Okay. Robot doing something. Okay. So at the end of the day, this is exactly what we want, right? We want the robot to do something. But now the question is, how do we tell the subsystem what we want it to do? How do we interact and tell the subsystem what we want to do? Okay, so how do we tell the robot, like as a driver, how do I tell the robot this is what I want you to do? What is our interface?
Be a control.
Yeah, Xbox controller. Okay, so over here we have an Xbox controller, like for example. Okay. Then so let's keep the subsystem over here. So let's say we have an Xbox controller. So for example, maybe an example is text is y axis forward. Let's say so. 6328. So let's say, and we'll get into what this tool is later. Here. Oh, it's not going to show up. Yeah, here. So like, see this Xbox controller. If we make this y-axis, so this joystick, if we go up, we want it to translate into something. So over here we have a command. Okay. So now how do we get this Xbox controller to tell this subsystem what to do? So what we know is there's an Xbox controller and then joystick command. Okay. So how do we bridge this gap?
You gotta tell through code what each button does.
Mm-hmm. So we have mapping, a mapping logic, right? Because you can think of, if you think of all of this as a black box, right? This human interface is going to be human doing something, right? So the input is the human doing something. Then there's this Xbox controller, and then out comes joystick command. And it can be like a Boolean, like a button, or it can be a double, which is like a joystick, right? When you have a button here, when you click the button, that's a Boolean, right? It's an on or off, true or false. And then this joystick, there's a lot of kind of precision you can have. Either you put it full forward, and that's like, let's say 1, or you can do half, and that's like 0.5 or something like that. So this is how we can think of a joystick command, as a Boolean or a double. So yes, then as Kyle said, there's now what we have to have some sort of mapping. And what is the mapping? Can you explain that, please?
Mapping is just where you bind like certain movements on a controller to certain actions for the robot, right?
Yep. So for example, and we're almost done here of painting the entire picture. So this mapping, you can think of it exactly as you're binding the controller, the joystick, whatever, to a desired action. So now, what are some examples of subsystems that we have? We have intake, elevator, and so on. Right? Then there's drive. Okay, so there's many different subsystems. And then there's one other piece to the puzzle which is missing. And can somebody tell me, so what do you think the missing black box is between this mapping logic to the subsystem logic? It's a little nuanced.
Isn't it telling the components what to do?
What do you mean by that?
Like telling motors to move and stuff like that.
So that's what the subsystem should take care of.
Okay.
So this is what tells motors to do something. Okay? But there's a missing piece here, and that is, let's say you want, actually, so sorry, how do you pronounce your name? Is it Ralia?
Really.
Relia? Okay. So let's see if so let's see. Let's say I want my robot to grab a ball and raise the elevator. Grabbing a ball is kind of the intake. But the raising, let's say, raising a claw, for example, is an elevator. And so those are two different subsystems that have to work together, right? Because when we talk about subsystems over here, we're talking about an intake, this is what you need to do. An elevator, this is what you need to do. But there's kind of this missing piece of like coordinating of multiple subsystems together. So there's this missing piece of like there's this missing piece between the mapping or the binding the controller to the desired action to the individual subsystems, and you can think of it as kind of like a coordination layer of multiple subsystems together. So then you say, okay, this subsystem needs to do, so a desired action might be like follow a path and score and score. Right? So this is going to be this coordination of multiple systems together. That's going to like generate different commands, one to the intake, one to the drivetrain, and one to the, let's say, claw. Right? So that's what this layer is. And then this layer over here is, well, the drivetrain, I told it to do something, so it has to do it. And then this claw, I'm telling this to do something, and it's responsible for doing it. And so this is kind of like the main flow that we're going to see in code. Okay? Are there any questions here? Okay. So now we're going to actually go into the code. And I don't really know the best way of going about this. So I think we should start with, so we've already looked at subsystems, and now I think we should start with the first piece. Let's try to start at the beginning and move our way over here in this direction, okay? So, an Xbox controller, maybe. So, okay, I'm just going to describe this. Okay, so at the top of our program, would you like me to continue using diagrams, or would that be helpful, or just by looking at the code, can you guys start to understand what's going on? Like, I'm happy to do it more with charts or more with the code, depending on how you want.
I say more with charts, just because it's a little bit easier to visualize.
Sure, awesome. So now let's actually start to understand robot code structure. Okay, and part of this structure is imposed by WPI lib. And when I talk about WPI lib, what that is first gives you a lot of code already written for you, such that your program can actually just simply use that pre-built code. Okay, so that's WPI lib. Okay. And then there's a lot of code structure, which is all dependent on how we want to organize our code. So I guess a good point to make about that is some structure is enforced and some structure is up to us. Okay? And when we say it's enforced, that comes from WPI library. And this right here is our code organization. It's all about how do we organize our code in a very simple manner, okay? Such that it all makes sense and all that. And every team does it different. So, what's enforced at the top level is what we call timed robot, okay? So you'll see here at the top of our code, so in the file structure, there's a file called, when your robot turns on, it calls this main file, okay, main.java. And all that does is it says, it runs this function called main, and it says robot-base.startRobot, okay? And what that start robot thing does is it goes to this robot.java file. And at the top of robot.java is a class called robot. And as you see here, it extends what they call timed robot. And you'll see that most robots, like here's 254's code from 2022. You'll see that they have main.java. You see it's exactly identical to what we had in our code. And here's their robot. And you'll see that they have their robot extends timed robot. This is kind of like what everybody uses, okay? And so now let's look at what timed robot does, okay? So in a high level sense, there are 3 modes, okay? One, the first mode is autonomous, and that's like the first, 15 seconds, I don't know what it is. The first 15 seconds of the match. And then there's teleoperated, which is the rest of the match. I guess let's consider it as 2 modes. Okay. So there's 2 modes. There's autonomous and then teleo. Does that make sense to everybody? Are you familiar with this? Okay. So in autonomous, I mean, okay, so we won't go too much into it, right? But autonomous, you can't control the robot with a joystick, with an Xbox controller. You have to like pre-program the functionality. So instead of the input being a human doing something, in autonomous, you have to like pre-program kind of like scenarios that your robot will actually follow. Okay. And then in teleop, you can use the Xbox controller. And if it'd be really cool, and I think we can get there, we can have our autonomous like take in vision data from a camera and use the April tags to like track where it is on the field, and you can do some really great stuff, and then we'll get there. And then there's teleop. Okay, in each of those modes, there are different states. Okay. In each. So there's different states in each of the modes. And so the first state is the init stage. The second is the periodic stage. And then the third is kind of the, what do they call it? Periodic. Let's not go into their code because their code is usually very complicated. Team for teaching, SRC, main, Java, robot. Perfect. So there's, I guess, just init and periodic. Oh, and then there's another mode called disabled. Okay. So there's different states, init and periodic. So as you can see, what happens, and we'll see it in just a second, is there is so for each of the modes, you have init and periodic. Okay. And so what we'll see in the timed robot class, remember, we are talking about the timed robot class. You'll see here, there's code called, I guess, then they have like, so robot init is special. So let's look at the modes that we can hook into. So there's something called robot init, robot periodic, auton init, auton periodic, teleop init, teleop periodic, disabled init, disabled periodic, and then they have a test one, and then a simulation one, which we can get into later. So, could somebody tell me what each of these functions does? What do you guys think these functions do?
Isn't init like as soon as that function is called, and periodic is every, I forget the exact time, but it's like consistent. It keeps running.
Exactly. So what you can do is you can think of you could think of it as you have an init is called once. This is called, and then you have periodic. Okay. So when you've entered a given mode, so that in the life cycle of a mode, you start, when you start the mode, whether it be auton, teleop, or so on, the first thing that's called is the corresponding init function. Okay? And then after that, the periodic function is called, and it runs in a loop. Okay? And this loop, as you said, is default is 20 milliseconds. Okay? So what happens is when you enter auton, right, the first thing that's called is your init, and then your periodic function, whatever's in that function is called, and then 20 milliseconds goes by, and then in 20 milliseconds, this periodic is called again, and then it runs in a loop. And then as you stay in auton, you just loop through this periodic code. So here you would put all of your code related to initializing your auton, and then whatever happens in here, this is what happens during auton. Okay. Same thing for teleop, init, and periodic, and so on. Does that make sense?
Yeah.
Okay. Seems this chart is pretty cool, yeah. Okay.
Yeah.
So now we know what the timed robot class is. Okay. And this code I have working right here is it actually is a working implementation of an ARM, which I showed in Slack. Right? I had like a little video thing here. This is what this code was running this. So if you look over here, there's like a little square, and when I press a button on my keyboard, it lights up, which is like a trigger, and it makes this arm go up. One more time. See, up and then down, whatever. Okay. So you'll see that this robot init, this is called, again, it's the same kind of life cycle as, it follows the same life cycle of init and periodic. But this init happens right when you turn on the robot. It's called once. Okay? And then this periodic is run also. And so you can see that in Teleup init, I don't have any code. In Teleup periodic, I also don't have any code. But so the question is, how did I get this thing to actually work, right? Because over here, you see I'm on Teleup. But if you look at the code, there's no code running in Teleup periodic. And so that seems not, from what I've told you so far, that doesn't make any sense, does it? It doesn't make sense.
No, it doesn't.
So, by the way, I've never programmed a robot before. So when I, like 2 or 3 weeks ago, I was looking at people's code and they had like no code in Teleup periodic. I'm like, what? That doesn't make any sense. And then I realized, or I learned, and actually, First Robotics, they have a Discord chat where there's many different teams. That this guy Peter, he's the one who programs WPI-lib, so he's literally the person who makes the stuff. And there's people from so many different. And you see here, this is me. I'm asking questions and stuff like that. So I do encourage you guys to sign up to this Discord channel, and then you can literally ask any question. They're super friendly, and it's all people in first. Okay. So by asking around what's going on here, they explained to me the following concept. So as we did over here, so here's the interface, and then there's FRC event WPI-lib command-based program. Okay. So let's read this together. Okay. So this is I guess going back for a second. Over here, we have we said that robot code structure, some of it is enforced, and some of it is up to us, however we want to organize the code. Okay? One example of something that is effectively enforced is this timed robot class. And then there's kind of like a framework by which first says you can kind of get all of this to, I guess, get this section right over here, how you can orchestrate this section, which is called command-based programming. And again, why I didn't jump right into this and why we decomposed this is you're going to see that command-based programming is effectively solving exactly what we have here. There's a mapping layer, there's a coordination layer, and then there's the individual subsystems. Okay? As I said earlier, it's so important that this is all very intuitive, and if it's not, we have to take a step back. Okay? So before we get into command-based programming, what are some questions that you have? Or do you have questions?
I don't have any questions currently.
And anybody else?
I don't have any questions.
Okay. So command-based programming. Can you guys read the screen? Or you can see it?
Yes.
Okay. So what is
Yeah.
command-based programming? So WPILib supports a robot programming methodology called command-based programming. In general, command-based can refer to, general programming paradigm, and it can also refer to how WPILib kind of like uses this term. Okay? Command-based programming is one possible design pattern for robot software. The design pattern, again, is how we choose to structure our code. It's not the only way to write a robot program, but it's very effective. It tends to be clean, extensible, and you could potentially reuse it from year to year. Okay. It's also known as declarative programming. And in declarative programming, what do they say? Yeah. It's a style of software which focuses on describing what a program should do as opposed to how it should get done. So you can tell the robot, so there's two ways of telling a robot to work, right? There's either you can say tell elevator to go 30 inches up, and then tell claw to open, right? So this is one way of kind of like scoring, okay? Or what you can do is you can say, and this is saying what needs to happen. And this makes a lot of sense. Versus, on the other hand, how it should happen is saying motor 1 should turn on at 50%. Check encoder. Check encoder and key, and then shut off motor 1 after 30 inches up. And then open solenoid. Okay? So these are two ways of programming. You can say tell the elevator to go up 30 inches and then tell claw to open. This right here is very declarative. You are declaring what you want to happen. And then the implementation details, you leave that for the actual intake, elevator, intake, whatever. Versus how it should happen is, okay, how do I tell the elevator to go up? Okay, turn on motor at 50%, blah, 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 blah. So do you see how declaring what you want to happen is very nice? And it makes much more sense.
Yeah.
Okay. So that's what command-based is. The command-based library allows users to define desired robot behavior while minimizing iteration by iteration. Okay, whatever. So the first concept is the concept of, where is it? Triggers. Okay. And that is this right here. This is called a trigger. Okay. Maybe I'll put that in blue. Okay. So this blue is going to be the concept in the code. So you see trigger here. That's this concept. Again, nothing new. We're just putting some more meaning to it. So trigger. It should bind the controller to a desired action. And let's see how that happens. So what we can do is we can call new trigger. Okay? And what this is some sort of condition that should trigger an event. In our case, this is going to be a joystick. Okay, so an Xbox condition right here is going to be the kind of the source of the trigger. Okay. And then there's kind of like, okay, now what do you want to do with that trigger? Okay. So if we go into the code, I have right here, so this this right over here, you're gonna actually start to see how this works. Okay. So what I did was I created a trigger. I call it trigger. And I define it as the Xbox controller. So here I'm defining an Xbox controller on port 0. So I guess if you have multiple controllers, you can like go like this. And Xbox 2, and that's on port 1. So you can define your controllers over here. Okay? And then what you say is, okay, Xbox, get me the button, I guess button number 1. I think you can do Xbox controller dot, yeah, look, you can do button, and then you can do the KA, okay? Is it dot value? Yeah. So here, what you can do is you can say, okay, this trigger is going to trigger when the A button is pressed, okay? And that is the button 1 here, okay? So up until this point, I've created a trigger, which is bound to the A button. And now what I can say is if I do trigger dot, look at all of the options that I have, okay? So what you can do is in the code, in the documentation, you have on true, okay? So I can do on true. Okay, what does this mean? Let's look at it. And it says if you bind a command, and we'll get to that in a second, to the on true event, when your button is pressed, it'll start the given command whenever the condition changes from false to true. Okay, let's look at while true. Okay, so for example, let's start to look at let's look at the trigger. Okay, so some of the events are on true, and another one is while true. I want you guys to work together to understand what both of these do and why I would use one over the other. So hold on. Here. So on true. Maybe I should just delete that. Okay. On true. While true. Okay. So can you guys work together to tell me what this on true does and what this while true does and what the difference is?
My guess for on true is it only does it once, and while true keeps repeating it while the button is pressed down or whatever.
Yeah, give me just a sec.
Mike, hold up. No, sorry. Okay, I'm back. My guess for on true is it only does it once when the button is pressed, and then while true keeps repeating the action while the button is held down.
Yep, exactly. So if we go to our handy dandy Excalibur, we can maybe do something like false, true, 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 and false. Okay, so let's say this right here is time, okay? and this is, let's say, bound to the A button. Okay. So if it's false, 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 and then there's some trues and then falses, I want to know on true and while true. Okay. So can you tell me when this on true? It's Ralia. Is that how I pronounce it? I'm so sorry. Ralia, okay. Ralia, sorry, I'll get it. So can you tell me when this on true will execute the code versus when while true will execute the code?
I believe that on true is gonna start working the code on the first true and all the other trues, but it will go once and then pause and then read the true again and then continue. But while true, it's gonna keep going continuously until the end of the trues.
So you're saying this, the while true is gonna execute code here and here and here and here?
Yeah.
Okay, and is this on true correct, or do I have to modify something?
I'm not sure if this is right, but I feel like on true is it's gonna be similar to while true, but it's gonna have like pauses, like breaks.
Okay.
And
Yeah, so let's look at the documentation again. And the actual code implementation, their documentation is amazing because it tells you, so let's read it again. On true, can you read this please?
yes, it says starts the given command whenever the condition changes from false to true.
Okay. With that being said, can you validate or say what's wrong with this on true here?
Oh, okay. So then that means it'll only play once.
Exactly. So this is exactly while true versus on true. Remember, this is still times robot class, and it works as init. So inside of the Auton or Telia, it runs this init code, and then it keeps looping through this periodic code. Okay. But what's great about this is kind of this framework is how would you actually program this on true? What you would have to do, and I'll just kind of give you the answer, is you have to keep track of last value and current value. Okay? So how this trigger actually works. Actually, let's see if their implementation makes sense. No, it's kind of, yeah, here, look. So let's actually look at the on true, right? When it changes from false to true. And let's try to make sense of it. So this mloop.bind, this is basically hooking into this looping logic. Okay, that's what this mloop is doing. And it says, look at here. What it's doing is it's saying, get me my last value. Okay. And if my last is false and my current is true, then perform the command. That's how this works. That's how this on true works. What you have to do is you have to compare the last value to the current value. If the last value is false and the current value is true, only then do I schedule the command. Does that make sense how on true would work? Okay. And now how do you think while true works?
Is it just like while this button is held, keep repeating this same action?
So let's look at it. mloop.bind, right? It hooks into the looping logic. I guess they're keeping record of the last time, but I don't know why. Oh, got it. Okay. So what they do is they get the current value, right? Once they have the current value, okay, so if my last value is false and my current value is true, so the same exact logic as in the onTrue, I'm going to run my command. But then if my last is true and now it's false, I want to cancel it. Okay, so could somebody make sense of what this is saying here?
I think it's saying that the command is gonna continue going until it turns false.
Yeah, so if in this case, when it goes from false to true, it runs the schedule, and then it doesn't do anything effectively until it goes from true to false. And look, if the last loop is true, and my current one is false, I want to cancel the command. Whereas in the onTrue, what does this do? It's saying, okay, look, in the onTrue, what it's doing is it's scheduling the command, but it's not canceling the command. So that's interesting. I actually didn't really know that. So here, maybe as an arrow, this cancels command, and this schedules command. Isn't this kind of cool? We can actually look at the implementation and see what it's doing. I think that's pretty cool. Okay, so that's what while true and onTrue is. This onTrue, though, means that the command is never canceled. Okay, so that's interesting. So let's actually start to understand what is a command, right? Because this right here, these are triggers. Okay, so these are a few of the different triggers, while true and onTrue. But what does it run? It runs what we call a command. And that's the next part of command base.
Wait, I have a quick question.
Yeah.
If the onTrue command is never canceled, would that mean it just keeps running forever?
Interesting. So we will get into that, right? Because that's a very good question. We need to see what a command is first, right? To see it's a very good question. It is 4 o'clock. I can go a little longer, but I want to be respectful of your time. If you guys can stay, great. If you can't, or if you don't want to, that's also great. So do you want to continue for another 20 minutes, or should we conclude here?
I could stay until you're good to leave.
Okay. Raelia?
We can keep going.
Okay, sure. I just wanted to be respectful of that. Okay, so we know what a trigger is now. So this is kind of this is how we can bind an Xbox controller to something. And so this desired action, what is the technical term for this in program, in what we just saw?
Command.
Exactly. Okay. The input is a trigger, the output is a command. Remember, input, output, input, output. Okay? So let's actually now, and we're going to go into the actual code in a bit. But first, let's read the documentation. Okay, so this is declarative, right? You say, when this button is pressed, do this. Versus, in contrast, without command-based, the user would need to check the button state every iteration and perform the appropriate action based on the state of the button. This is exactly what the trigger is doing, right? If true, if your pass was false, then do something. If not, so that's exact. Does this logic make sense?
Yeah, it's just a shorter way of writing it, correct?
Yeah, it's doing this logic for you. Because at the end of the day, remember, we are in infinite loop, basically, that repeats every 20 milliseconds. And now the question is, do you want to hold on to this logic, and do you want to do this yourself? Or there's this concept that they've already, this abstraction called a trigger, which does this for you. Cool? Because at the end of the day, you can't get away from actually performing the logic, but it's who's doing the logic. And so anyway. So now the next thing is subsystems and commands. Okay. So subsystem over here, this looks exactly like what we're working on now, or what we have been working on. Drivetrain, elevator, arm, blah, blah, blah. So we already understand how subsystems work a little bit. And then over here, look, these are commands. And this is the command, the same command that we're already starting to become familiar with. Okay, so you see how it's slowly starting to make sense a little bit?
Yep.
So, with that being said, could you guys start? I have to, I'll be back in like 1 or 2 minutes. Does somebody want to start reading and discuss amongst yourself? Or
should we get on that website?
yeah, I can put it in the Slack. And I'd actually love for you guys for me to stop sharing in like 1 or 2 sessions. So I want one of you guys to start taking over. So maybe if you could share your screen, or somebody, Radia or Kyle, if one of you want to share your screen, and we'll all kind of follow along.
I'm open to do that.
Okay, whatever you guys would like. I'm gonna stop sharing my screen as well. And I'll be back in like a minute or 2.
Like the drivetrain, which drives, the wrist, which like moves, elevator, which brings game pieces up and stuff like that. So how commands are run? Commands are run by the command scheduler singleton, which I don't know what that is. I'm gonna have to Google it real quick. It's a software. I'm gonna pretend like I know what that is. It pulls triggers for commands to schedule. The scheduler's run method must be called. It generally is recommended to call it from the robot periodic, which makes sense because robot init is just it's only called one time, while robot periodic is called every 20 milliseconds. It's run at a default frequency of 50 hertz. Multiple commands can run concurrently as long as they don't require the same resources. Like, you can't be driving forward and turning at the same time, because those are those both use the same motors, unless they don't. But
Sorry. One thing to interject for a second is you can have a command called drive, which like it's at the subsystem level. So if you have one command which is let's say it's path following, right, on your drivetrain. That uses your drivetrain versus manual control. That also uses your drivetrain. So if you have a command for path following and a command for using your joystick to drive robot, do you see how those two commands can't operate at the same time? Because they use the same subsystem. So you should start thinking of it as what subsystems does this command require?
got it.
Okay, continue.
Where were we? Resource management is handled as on a per subsystem basis. Commands specify which subsystems they interact with, and the scheduler will ensure that no more than one command requiring a given subsystem is scheduled at a time. Does that mean, like, let's say we were to have the Pathfinder and operator controlled drivetrain running at the same time, would it like take priority over one and then do the other one later, or will it just completely cancel out the other one?
Yeah, very good question. I actually don't know the answer to that. So the question is, if there's a command that's in process, that it's running, right? That where it kind of takes control over the drivetrain. Let's say it just takes control over the drivetrain. You have another command that also takes control over the drivetrain. Does the second one kind of like steal the drivetrain from the first command or not? I don't know. My thought is, we can actually look into it. So let's finish this page and maybe we'll look into it. Let's look into the code. So finish this page, and then I want Aurelia to kind of summarize what we've discussed on this page, and then I'll take over and show you some more of the code. But I
got it. My guess would be it would steal it, because that would be more advantageous, because it's a new command, and it would make sense if the new one took over for the old one.
That makes a lot of sense, actually.
That's just my thoughts on it.
Yeah, that makes a lot of sense. We'll look at how it does it.
Got it. This ensures that users will not end up with two different pieces of code attempting to set up the same motor controller to different output values. Command composition. It is often desirable to build complex commands from simple pieces. This is achievable by creating a composition which is multiple. Composition is just a collection of smaller component entities, which is just components of commands. The command-based library provides several types of command composition for a team to use, and users may write their own. Command compositions are commands themselves. They may be used in a recursive composition, which is a type of composition in which the composite object may contain components of the same type as itself. Command group may contain one or more command groups.
There's something in programming called recursion, and that's essentially, it's a huge topic, but of course it's all about the intuition. It's that a command, so a command is a single, is a unit, and can't go lower than a command. right? But then you can have some commands that are more complicated, which use smaller commands. So you can have a command that uses that says, okay, I want to first pull this command, and that command says, I want to first pull this command. If that makes sense. So it's like a command can call a command can call a command. So that's kind of the idea of recursion.
Alright. Moving on, that is to say, one can create a command composition from multiple command composition. This provides an extremely powerful way of building complex robot actions from simple components. Alright, next page.
Let's stop here for a minute.
Alright.
And actually, the next page does make a lot of sense to go over. So first, go back a page. And Radia, could you summarize what we discussed here?
Yeah. So we went over the command-based programming, and they're made up of subsystems and commands, where the subsystems are different components of what you can control, and your commands is what those subsystems can do, such as moving forward and scoring and things like that. And then we went over how the commands are run, which they are run by command scheduler and are triggered by things such as buttons. Like we went over the example with the A button. And after they're called, they could be, I'm not sure if I remember this right, but there's something with the periodic, which allows it to run like multiple times continuously.
Yeah, exactly. So first of all, that was very good on both of your parts. I think it's spot on. I'm just taking control of the screen for a second, so if you can still see my screen. Can you see my screen?
Yeah.
Okay. So let's. Oh, do you see it? I think you have to go into. Okay. So exactly. So the first thing that Radia mentioned was okay. So going back to the top of the program. Remember timed robot. I said that I don't have any code inside of teleop periodic or teleop init. Can you guys now answer why I don't need any code there?
Would you already have it in the robot init and periodic?
Okay, so what actually schedules the commands? Radia mentioned it. The command scheduler. So what happens is you'll see that there's a robot periodic here, and there's a teleop periodic. So what happens is, well, robot periodic happens on any type of periodic. So it happens for auton periodic and teleop periodic. So what happens is every single time we enter this loop, we actually run the robot periodic and the teleop periodic. So I don't need the code inside of teleop periodic, right? Because if I had this command scheduler inside of teleop periodic, then my commands wouldn't work in auton periodic, and that's an issue. Does that make sense?
Yeah.
Okay.
I'm confused on what they mean by it won't work in Auton.
Sure. So basically, here's this periodic, right? So what we can actually do is we can actually break this down into so there's robot periodic, and then there's mode periodic. Okay, so the periodic, maybe I can go like this. So the periodic phase can be broken down into robot periodic and the mode specific periodic. Right, so if I want my command scheduler to operate on any single periodic loop there is, irrespective of the mode, I can put it inside of robot periodic. And that's what I want, right? Because if I'm in Auton or in Telia, I still want to schedule the command. Do the command scheduler. Does that make sense? Additionally, I could put the logic here and in here. That should also work. Right? Because if we look over at this periodic, what's run first is robot periodic, and then Auton or Telia periodic. Is that clear? Or are there?
Yeah.
Is it confusing?
It's not totally confusing.
Okay, but
It's
it's
still some aspects of it.
That's fine. So I guess let's revisit that in a second. So the answer to the initial the question from earlier is how is my code working when there's nothing here? It's happening over here. So this command scheduler. Now let's see. What were we trying to do again? So we were talking about subsystems and commands, triggers, how commands work. Okay, so two things. The first thing is we can draw another diagram, which we like our diagrams. So now if we think of the flow in a different way, we have a trigger. So human controller or Xbox controller that calls a trigger. That trigger commands. Right, the trigger schedules commands. And remember, as we said, a command can also it can call other commands inside of it. And then the commands issue issues commands, or it issues actions to be performed by the subsystem. So this is another. This is using more of the coding terminology as we just said, and this is the flow. So does trigger commands and subsystems make sense, and do we see how each of the how it all flows together?
Yeah.
Okay. So now let's actually see how going back to the question that Kyle mentioned. What was the question again?
If on true is never canceled, how does it, or why does it not keep going until it is eventually canceled?
Okay, so we just said, so the question is, in the onTrue, we issue a schedule command, but we never cancel it. Okay. So that's the question. While in the whileTrue, when the button stops being pressed, we cancel the command. Okay. So for that, let's move on to the next page. And Raylia, would you be able to share your screen and go through it, and we'll all kind of pitch in?
Yeah, hold on.
Okay. So I'm gonna stop sharing and mute myself, and I'll have another like 20 minutes. Isn't this cool how it's starting to come together?
Yeah, it's going full circle.
Yeah. And then once you get all of this, like how this actually works, then it's just like now you understand how the robots are all of them are programmed. Now it's about like, you know, it's really not hard, but it requires kind of a good conceptual model. Let's see.
Do you see the screen?
Yes, I do.
So, commands represent actions the robot can take. Commands run when scheduled until they are interrupted or their end condition is met. Commands are represented in the command-based library by the command interface. The structure of the command. Commands specify what the command will do in each of its possible states. This is done by overriding the initialize, execute, and end methods. Additionally, a command must be able to tell the scheduler when, if ever, it has finished execution. This is done by overriding the isFinished method. All of these methods are defaulted to reduce clutter in user code. Initialize, execute, and end are defaulted to simply do nothing, while isFinished is defaulted to return false, resulting in a command that never finishes naturally and will run until uninterrupted. Initialization. The initialize method marks the command start and is called exactly once per time a command is scheduled. The initialize method should be used to place the command in a known starting state for execution. Command objects may be reused and scheduled multiple times, so any state or resources needed for the command's functionality should be initialized or opened and initialized, which will be called at the start for each use, rather than the constructor, which is invoked only once on object allocation. It is also useful for performing tasks that only need to be performed once per time scheduled, such as setting motors to run at a constant speed or setting the state of the solenoid actuator. Execution. Execute method is called repeatedly while the command is scheduled. This is when the scheduler's run method is called. This is generally done in a main robot periodic method, which runs every 20 milliseconds by default. The execute block should be used for any task that needs to be done continually while the command is scheduled, such as updating motor outputs to match joystick inputs, or using the output of a control loop. Ending. The end Boolean uninterrupted method is called once while the command ends, whether it finishes normally or it was interrupted either by another command or by being explicitly cancelled. The method argument specifies the manner in which the command ended. Users can use this to differentiate the behavior of their command and accordingly. The end block should be used to wrap up command state in a neat way, such as setting motor back to 0 or reverting a solenoid actuator to a default state. Any state or resources initialized and initialized should be closed end. Specifying end conditions. The isFinished method is called repeatedly while the command is scheduled. Whenever the scheduler's run method is called. As soon as it returns true, the command's end method is called and ends. The isFinished method is called after the execute method, so the command will execute once on the same iteration that it ends. Command properties. In addition to the 4 lifecycle methods described above, each command also has 3 properties defined by getter methods that should always return the same value with no side effects. Get requirements. Each command should declare any subsystem or controls as requirements. This backs the scheduler's resource management mechanism, ensuring that no more than one command requires a given subsystem at the same time. This prevents situations such as 2 different pieces of code attempting to set the same motor controller to different output values. Declaring requirements is done by overriding the getRequirements method in the relevant command class by calling addRequirements or by using the requirements varied Java initializer list parameter at the end of the parameter list of most command constructors and factories in the library. As a rule, command compositions require all subsystems their components require. Runs when disabled. The runs when disabled method returns a boolean /bool specifying whether the command may run when the robot is disabled. While the default of returning false, the command will be cancelled when the robot is disabled and attempts to schedule it will do that. Returning true will allow the command to run and be scheduled when the robot is disabled. Important: when the robot is disabled, PWM outputs are disabled and can monitor controllers and motor controllers may not apply voltage regardless of runs when disabled.
So very quickly, so that apparently this runs when disabled. If you return true from it, then this command, even when the robot is disabled, it can still run this command. But then you're like, well, I can just, then I can run my motors when I'm disabled. No, this important block right here is saying that even if you're running a command when the robot is disabled, the computer will reject any like motor outputs. So you can't actually control a motor when you're in disabled, even though this is running. That's what this important thing means. Continue.
As a rule, command compositions may run when disabled if all the component command set runs when disabled as true. Get interruption behavior. The get interruption behavior method defines what happens if another command sharing a requirement scheduled while this one is running. In the default behavior, cancel self, the current command will be cancelled and the incoming command will be scheduled successfully. If cancel incoming is returned, the incoming command scheduling will be aborted and this command will continue running. Note that get interruption behavior only affects resolution of requirement conflicts. All commands can be cancelled regardless of get interruption behavior. Note: this was previously controlled by the interruptible parameter passed in scheduling a command and is now a property of the command object.
So, very quickly, this is the answer to your question, Tyler. So you can tell the command what should happen if somebody else comes in and another command comes in, right?
Yeah, that makes sense.
Yeah. So this is cool. I actually didn't know this. So continue.
This property can be set either by overriding the get interruption behavior method in the relevant command class or by using the with interrupt behavior decorator. As a rule, command compositions are cancel incoming if all the components are cancel incoming as well. Included command types. The command-based library includes many pre-written command types. Through the use of
Lambdas.
lambdas, these commands can cover almost all these cases, and teams should rarely need to write custom command classes. What are lambdas?
Yeah, it's kind of like if you go down for a second, I'll show you what it looks like. Go up, sorry.
Oh,
Yeah, to where it says lambda, and then go to the next code example. Yeah, so go down just a little bit.
sorry.
It's okay. Yeah, so stop. So see on line 28 right there? See this dot run once, and then there's parentheses. And then right away there's like open parenthesis, close parenthesis, and then the arrow. That right there is called the lambda. And basically, it is a shortcut for creating a function. Let's just keep it at that. Like you'll see how it's used, and then you'll be like, okay, it's kind of weird. Maybe you can go to the lambda. It's highlighted. It's in blue, so maybe you can click on it. Yeah, lambda expression. Maybe they have better. While method references work well for passing a function that's already been written, often it's inconvenient, and then you can use a lambda. So go back for a second, please. See right here, go up to the previous code right there, stop. Do you see it says command-based? Here, hold on. Oh, okay. So it says command-based non-interruptible equals commands.run. See this intake : activate? This intake right here is a class or is an object, right? But we've been discussing. An activate is a method that's defined on the intake. So what you're doing is you're passing into the commands.run. You're passing in the method that's defined on the intake class. If you have, and so you're like giving this command.run access to call this method called activate. Does that make sense? But if you go down a little bit, so stop right there. So where this lambda is defined on line 28, this like add hash solenoid dot set k forward, you don't have like instead of having to create an entire class, like a dummy class, so that you can pass that method as a reference here, just like you did above. You can like as a shortcut, you can write this lambda function here. So you don't have to create a dummy class and then create a method on that class, and then now you can pass that method into this run once function. Does that make sense? It's kind of like a shortcut. So that's what it is. Good question.
Many of these commands are provided via static factory functions in the commands utility class Java or in the FRC2 at cmd namespace defined in the commands.h header. Classes inheriting from subsystem also have instance methods that implicitly require this.
Okay.
Running actions.
Mm-hmm.
The most basic commands are actions the robot takes, setting voltage to a motor, changing a solenoid's direction, etc. For these commands, which typically consist of a method call or two, the command-based library offers several factors to be construct a method, inclined with one or more lambdas to be executed. The run once factory backed by the instant command class creates a command that calls a lambda once and then finishes. The run factory backed by the run command class creates a command that calls a lambda repeatedly until interrupted. The start end factory backed by the start end command class calls one lambda when scheduled and then a second lambda when interrupted.
Okay, so let's look at this example here. So the top example is let's do this, right? So this grab hatch command. So this is running once. So it's like when you're setting a solenoid or something, you just want to run that command once because you set the solenoid and then you don't have to do anything. Whereas if you go down, another use case is run command. So for example, if you want to run this command called arcade drive over and over again, right? Then you can, right, when the joystick inputs are different, then you want to keep calling this arcade drive, so you can do that. And then down is this command.start end. So this is basically saying at the start of the command, you can set the shooter to 50% power. But then when you let's say let go of a button, it'll run another command, right? Set the shooter's speed to 0. So you can see how there's different types of commands depending on what you're trying to do. Does that make sense? And they have different behaviors. They have like, do I want to run it once? Or do I want to keep running it over and over and over again? Or do I want to do something until the very end and do something else? So this gives you kind of like a nice language to express all of those different use cases.
Read what's at the bottom.
Yeah, and then I'll share a screen and then we'll kind of conclude.
Okay, got it. Functional command accepts for lambdas that full command lifecycle methods are runnable or std function void for each of initialize and execute, a boolean consumer / std function void boolean for n, and the boolean supplier / std function boolean for is finished.
Okay, so
A string.
yeah, I mean this is there's a lot of detail here, and I'm getting kind of I think that later, once we get more into commands, we can read the rest of this, because it is kind of like it's a lot of detail and it's kind of losing, for me at least, it's losing its you know what I'm trying to say?
Yeah.
So Kyle, in like, can you summarize what a command is? Kyle?
From my understanding, a command basically tells a specific part or component what exactly to do and how to do.
let's further clarify. What do you mean by component?
A component such as like a solenoid or a motor or like stuff like that.
So, no. Well, I mean, it can do that. You can, from the command, tell the motor to do something. But that's going back to, here, let me share my screen again. Going back to, do you see my screen?
Yeah.
Going back to here, which is robot code structure, some of it is enforced and some of it is up to us. I don't believe it's a good idea to, from the command, to tell the subsystem to do something. Sorry, to tell the motor to do something. Because a motor right, a subsystem kind of like owns a few different things. It owns actuators. It owns sensors. Okay. So what you just said, I believe, is that the command can tell the motor what to do. Right? And you could do that. Exactly. And so you could do that. There's nothing preventing you. There's many teams that do this, but it's not such a good behavior. What should happen? Exactly. And the subsystem will tell the actuator and the sensor what to do. So, does that make sense?
Yeah.
And so that's this right here is the majority of our program. Okay, this is how the program works at a high level. This is actually what happens, right? Where there's a loop that's running in the different modes. But this layer of abstraction that we're going to be that team 4. So let's just go into github.com team 4 elements. Let's look very quickly at last year's code. Okay, and you'll see. So this is last year's code. And you go here, you see we have a robot, we have our command scheduler, we extend times robot. In the robot periodic, we call this command scheduler.getInstance.run. So up until now, this should make total sense. Does it? Okay. Raylia, does this make sense, what we just saw so far?
Yes.
Okay. So already you're like leaps and bounds, like you can start to understand the code that we wrote last year. You can see how we have subsystems here. Okay. So last year we had an arm, a drivetrain, intake, I guess vision. And here you have the different commands that we created. So we had a drive command, and this drive command. So let's actually look into this, and then we'll end the video or end the thing here. So this drive command, it extends what's called the command base, which is the default for creating a command. The subsystems that it needed, right? A command requires subsystems. Here, we remember that add requirements thing, which tells the command scheduler this drive command is gonna like hold on to, is gonna require the drivetrain subsystem. Does that part make sense? Like it kind of makes sense with what we saw in the documentation. Okay. And then, so remember, Radia mentioned over here. Remember, there's the initialize, execute, and all the is finished, and then the complicated stuff down here. We'll see initialize. This is called when the command is initially scheduled. I guess we have no code in there, so we could have removed it because by default it's empty. Here's the execute code. So what do we do here? We ask to get the throttle. So this is going to go to the controller and get the, I guess we created a separate method called get throttle, which literally just, this is the driver controller, so right here. So see get throttle, gets the controller, which is an Xbox controller, and gets the left Y position, Y. So over here, it's, so how we drove forward was going up and down on this joystick right here. So that's, so this execute, so this right here is a double, which represents how much we go up and down on the left joystick. Here is a rotation. So I think we do it on the X joystick, the horizontal. Let's see. Yeah, get right X. So what that means is to turn, we have, if you go side to side on this joystick, then you'll get the turn as a Boolean. And then here, so then we call, see this right here, M drive, that's the subsystem. And then this arcade drive, right? We're not telling the drivetrain to, we're not commanding its motors. We're telling it, okay, run arcade drive. And that's exactly, for this command, we're following this behavior where the command tells the subsystem what to do. The subsystem is responsible for doing the actuators. And so this right here, look, here's an end. So this is called when this command ends. And I guess when this command ends, we're telling the drivetrain to reset its sensors. What does that do? Okay, so it's zeroing the gyro and resetting the encoders. And it is finished. I guess it's, we didn't even need this because it's returning false anyway. So I guess we're going to stop here. I think we covered a lot of material. And I think that you guys followed along very, very well. How was this for you?
This is a really interesting topic.
Cool.
And it
And
was also pretty easy to understand as well.
right, if you like break it down, it should be very intuitive. Right?
Yeah.
Radia, how was it for you?
I think, well, it's very understandable, and I feel like we really got more into the process on how we're gonna code a robot.
Yeah. Oh, was that a period?
Yeah.
Oh, okay, that's okay. Yeah, no, so definitely. I mean, I think that we did really start to understand how you're actually, like on a day-to-day basis or whatever, gonna code the robot. But I do hope that, like, starting way back here, right, from the translation 2D, it seems like, if I were to be put in your shoes, it seems like it would be a stretch to go from this code here to like how do I program the robot. But like I hope that you can see that there was like a progression from like going into the code to understanding what a class is and what an object is, and how objects are coming from classes, and so on. And then, what is this? This is more of the same thing. And then we go over here to subsystems, and we say, okay, subsystem is a class. And then you create, you initialize the subsystem and that's called an object. And then we go over like the hierarchy of the logic of like different, like there's different layers to the logic here. And then there's, and then we're like, now that we start to understand the intake, we take 254's robot, we say, okay, a robot is super complicated. So what you can do is you can break it down into subsystems, and then from the subsystem, you can say, okay, so we actually take the subsystem, where is it? Over here, and we say, okay, a subsystem is a collection or a class, right? Or in this case, a subsystem class, whatever, like an intake subsystem class, or any subsystem class is broken down into properties and methods. Properties can be thought of in relation to subsystems as sensors, actuators, and other variables if you need them. And the methods are actions that you can perform. And then once you understand those actions, then you start to go into how the robot works. You have a timed robot class which hooks into the different modes of the robot. And then in each of those modes you have init and periodic. And then we say, okay, well, the mode life cycle is init, and then it loops through periodic. And then we say, well, okay, where is it? Then this is kind of the logic of how you go from an input to an output of the motor. And you can see there's this like complicated like logic here, but it's all there for a reason. And then once you understand that, then you can start to go into, okay, there's a trigger, commands, subsystems, and actuators. And I think that there's all of this backstory and history that you need, but once you get there, you guys do have that knowledge now, that understanding. Now it's like, okay, I can program a robot. So that was kind of like the last couple weeks in like 10 minutes of like the map. But does that make sense?
Yeah.
Cool. So in our next class, maybe on Thursday, what we're going to get into is we are going to zoom into this system right here. Okay? We're going to look more into this mapping, or this part of the code. Okay? So how do commands issue like actions to the subsystem? There's something that Team 254 has pioneered, and a lot of teams now copy it, where it's called a state machine. Okay, just to give you guys a little bit of information. So, let's see if there's FRC state machine. Mario state machine. Yeah, here. Look, there's a good example. So here, just really quickly. Where's the picture? That's what I want. Open the imagery tab. So we're going to use this diagram to explain how a subsystem can go through different states, just like Mario can go through. So here, each one of these Mario characters is a different state. Mario can be just regular Mario, a Super Mario, Fire Mario, and Cape Mario. For example, a shooter, the different states of a shooter is idle, like it can be idling, which means it's not issued a command to do anything. It can be set to a certain speed, and so on. And this transition here, this is like the motor, issuing a motor, issuing a motor to go at a certain speed. So you can start to think of a subsystem as different states and transitions between those states. So that's what we're going to get to in the next class. But this is kind of like a teaser for you guys. And then after that, then I'm going to have you guys start programming. And we'll do projects, and somebody will take an arm, somebody will take an elevator, and so on. Okay? I hope that was useful. And I'm gonna upload this also to the YouTube.
Thank you for teaching us.
Of course, it's really my pleasure. Okay. Take care.
Bye.
See ya.